At first, I would like to thank you very much for inviting me to this exciting event. I really would like to have visited Iran again, but of course this is not possible due to the current pandemic situation. Therefore, my presentation will be done remotely, and afterwards I will be ready to answer your questions. Today, I will talk about cyber-physical systems and the Internet of Things. Especially, I will concentrate on aspects related to predictability and timing. Here you can see the usual way of representing cyber-physical systems and their interaction with the physical world. On the bottom, you see depicted how these systems may observe or control any kind of physical, biological or social process. On the top, you can see the virtual world, where we can reason about whatever we have been collecting from the natural processes. We can make decisions, and all of this is based on data analytics. Finally, the decisions in the virtual world can be used to influence the observed processes. There are many related examples, for example, industrial processes, biological processes in humans related to health, environmental processes related to air or water pollution, but of course also observing the behavior of humans. If we look now at deployed systems and their application domains, we can ask ourselves when keeping time requirements or deadlines is actually an important system property. In the following, I will concentrate on guaranteeing certain properties of cyber-physical systems, in particular how to provide guarantees in terms of functionality and timing. As you can see in this diagram, this concerns the observation of the physical world, communication with the deciding and reasoning entity, and the path back to influencing the process. Therefore, we are concerned with sensing, communication, and computation. Here we can see some especially time-critical applications. We have been working ourselves in some of them, mainly related to environmental monitoring, like natural hazard detection and air pollution monitoring. But there are many other applications where actually reliability and predictability are of major concern. For example, disaster management, applications related to human health, factory automation or cyber-physical systems that support mobility. This is just an example on which we have been working on. Together with Siemens Building Technologies, we have been designing the first wireless and certified fire detection system that is available on the market. It's a modular system where a fire alarm is transferred hop by hop through the whole network. Of course, for certification, you need to prove the reliability and dependability of the end-to-end system. One major aspect was its real-time behavior. That means that there is a hard time bound between detection of a fire and information to the host. At the same time, we have been dealing with high requirements in terms of long lifetime, as the batteries should last for several years. Our experience was that there is a long path between developing the methodological principles and algorithms on the one hand, and a working product on the other. The tremendous engineering effort was necessary. As you have seen, there are applications that require hard real-time, but possibly not so many. The next question is therefore, especially for these applications, can we really guarantee time bounds? If you look at the conferences and papers in engineering related to real-time systems, the answer seems to be yes. On the other hand, real-time processing is not only a matter of scheduling algorithms that run on some hardware. Correct operation, and this includes predictable behavior, requires many other prerequisites. For example, a correctly working hardware. No one is destroying the hardware. There should be enough energy available. There are no alpha particles that change operations. And sensors are reliably connected without too many connection failures. As mentioned before, we are deploying sensor networks in the Swiss Alps under extreme conditions. They are used for early warning of rock slides and rock falls and therefore need to be highly reliable. Events need to be sent to the public authorities within a short amount of time. On the other hand, the environment is extreme and therefore all elements of the whole pipeline between sensing, processing, local decision making, communication and post-processing are under high stress. Examples are extreme temperature variations, precipitation, rockfall, unreliable wireless communication and so forth. To summarize, it is impossible to guarantee time bounds in any reasonable installation. Real-time guarantees are based on the correctness of the underlying assumptions. And as a side remark, especially in the area of multiprocessors, the assumptions usually used in real-time theory are highly unrealistic. This concerns especially interference on shared memory and the shared communication infrastructure. Nevertheless, society will increasingly depend on cyber-physical systems and the Internet of Things. In order to have a high degree of acceptance in our society, dependability and trust are actually necessary. After these initial remarks, I will now talk about a few attempts to increase dependability, predictability, and timing behavior of this class of highly distributed systems. Well, we need to understand what are the reasons for the low reliability. Or we will, as we have explained already, the tremendous engineering effort that is necessary in order to design highly predictable and reliable systems. Let me point out two main reasons, but of course there may be many others as well. The first one is related to resource constraints that we very often find in Internet of Things systems. We are using local sensors and low-cost sensors. We have to deal with limited communication bandwidth. There's usually not sufficient memory available. Processing capabilities are limited due to cost and energy constraints. It is our all experience that reliability is in danger when the system operates close to its resource limits. I think you know all lots of examples in terms of exceeding the memory limit, buffer overflow due to limited bandwidth or number of packet drops, systems running out of battery and so forth. The second reason is related to the demand on adaptivity. There are many well-known concepts to construct reliable systems. They mainly come from avionics and automotive industry. Everything is partitioned and time-driven. One can partition the memory so that interference between applications via the memory is not possible anymore. One can partition the time in time slots, each one reserved for applications, for a single application, in order to avoid interference between applications in the time domain. But these static methods make it very hard to design systems that dynamically adapt to requirements. Examples are reacting to changes in the environment, user interaction, but also switching between different modes of operation, like power modes or mixed criticality operation. Adaptivity is a major requirement in many applications like surveillance, early warning, and industrial control. One example can be seen here. It is from the already mentioned early warning application in the mountains. We are operating several large-scale sensor systems here, and they use several modalities to observe the environment, for example, acoustic monitoring. The reason is that also mountains make noise if they don't feel well, like humans. And here you see a typical operation pattern. An acoustic event is detected after a local decision is made. And the event is then communicated to a host station. Based on the data that are related to this event, and possibly also whether other sensor nodes also detected an event, the host decides on relevance. Afterwards, the host may now instruct the sensors to switch on other sensor modalities like GPS or cameras. Then a high data rate communication will take place between the sensors and the host. All of this takes place under highly restricted resources like communication bandwidth, computation possibilities, and of course also energy. As a summary of this first part of my presentation, we can actually conclude that there are a few applications that require hard real-time guarantees. But on the other hand, almost all applications require a reliable operation. And what will be shown now are some new models and methods that make systems more reliable, and they also allow to provide bounds on essential quantities like time. With this, I come to some of these new models and methods. I decided to illustrate them using a complete cyber-physical system consisting of sensing and actuation of a physical process, and doing this with several distributed nodes, and then finally communicating everything through a low-power wireless network. In the end, you will see the whole application running, controlling a set of inverted pendulums. I will now go through the various elements of such a system and the corresponding methods in order to make the whole system reliable and timing predictable. Let me start with the wireless network. As a constraint, we would like to concentrate on low-power wireless networks. Again, here you see some of our own installations where we used the principles that will be described next. This concerns the wireless fire network, but also the installations in the mountains. Here you see depicted the locations of the various sensors on the famous Matterhorn in Switzerland. In this diagram, let us suppose that we would like to transmit an event from A to B. Let us suppose further that we are in a resource-constrained environment and therefore we use multi-hop communication and a multi-hop network. The examples I have shown in the previous slide are typical applications of this. As mentioned, we are in a low resource environment and therefore communication is unreliable. Let us suppose now that one of the connections is broken. As a result, the communication path from A to B is interrupted. In the classical, highly used communication protocols, the nodes know their environment and they know the identity of nodes that they can reach directly within one hop distance. This information is continuously updated in order to be able to react to this kind of disturbance. Here you see what such a network could look like after choosing another routing path. Again, choosing another routing path is a very complex operation that involves a large number of nodes that are unreliably connected. Nodes use their knowledge about neighbors and global knowledge about the direction to the sink in order to reroute the information that should be transmitted. But suppose now that suddenly two other links are broken. And now you can simply imagine that this leads to a very complex situation. Packets are underway, they have been rerouted, they need to be rerouted again without the knowledge whether the new path really reaches the destination. can we expect that this construction that is implemented in all of the commercially available protocols works reliably? Can we prove anything about it? Of course not. At least not if you suppose a realistic model of the environment that is highly complex and non-deterministic. Proving something like bounds on the packet reception or even timing bounds is virtually impossible. The reasons are obvious. We have a highly distributed state, and the state depends on changes in the environment. For example, the availability of communication links between two nodes. In addition, changes in the state have a long tail. That means the inference is long-lasting. As a consequence, bounds cannot be obtained, at least tight bounds cannot be obtained. But also, according to our own experience and experience of many others, these systems also don't work reliably in practice. Some time ago, we started working on a completely different communication paradigm. It is now widespread in the community. It is called glossy and based on something that is called synchronous transmissions. What is this, and how is it different from the usual wireless communication principles? Well, usually you try to avoid that several nodes send messages at the same time. The reason is very clear, because you try to avoid that you have interference between the messages and the receiver cannot decode any one of them. This principle is also crucial for the multi-hop communication I explained before. We drastically go away from this principle now. We allow that several nodes send at the same time. The prerequisite is that they send the same information with the same speed and at the same time. It turns out that if these conditions are satisfied, the receiver can decode the information reliably. Therefore, we have redundancy in time and space. We do not avoid interference, but we use it to our advantage. You can also relate this to communication on a bus. If several components put the same information on the bus with the same speed and at the same time, another component can easily read this information. In terms of wireless, this principle works for almost all low-power communication physical layers, like Zigbee, LoRa, and Bluetooth Low Energy. How do we use this basic principle to perform a communication in a larger network? The principle is shown here. A sender transmits its information, and a few nodes in its environment can receive it because they are close to it. They repeat this message totally synchronized with the same speed. This message is then not only received by the original sender, but also by some other nodes. These nodes do the same and repeat the message that is then received by a new set of nodes and so forth. The number of these elementary steps corresponds to the diameter of the network. And here you can see how this principle can be used in order to provide an overall communication scheme for low-power multi-hop networks. The communication happens in rounds that are separated by silence. The silence provides the opportunity for nodes to switch off their power and to save energy. Each round now is partitioned in time. It starts with the transmission and availability of the schedule of the round, meaning at what time the nodes are allowed to transmit the information. At the end of the round, a new schedule is broadcasted to all nodes in the network. In particular, this schedule contains information when to wake up again, and as a result, all nodes wake up for the next round synchronously, and they can sleep in between. But this scheme also allows that the time between two rounds can be adapted from round to round. To this end, nodes may send their communication demand to the host. The host decides on the distribution of the available time and communicates this with the new schedule. Here you see that every of these time slots within a round corresponds to a flooding. And the flooding that I described a few slides ago. For example, the first data slot is assigned here to node N1, and the node uses this time slot to globally distribute its information. At the end, you see that the new schedule is distributed by a node NN, which is our host. In summary, you see how we fight the difficulties in reliable and timing low-power wireless communication. We make use of the interference instead of avoiding it. At the same time, we leverage the experience from real-time processing by partitioning the schedule in time. But in addition, we do not use a fixed schedule, but add a high degree of flexibility. We can dynamically adapt the time between two rounds and therefore the aggregated bandwidth. And we can dynamically adapt the time each node has to transmit its information. This combination of adaptivity and offline guarantees allows for a robust and predictable communication scheme with provable guarantees. And most importantly, it is highly energy efficient. Based on this principle, one can now go on and provide more predictability and timing results, including distributed consensus and highly precise estimations on reliability and energy consumption. As a short glimpse, I decided to say a few words about hard real-time guarantees under the mentioned adaptivity and low power requirements. In general, there are three problems to solve. Namely, at first, determine when the next round starts, and allocate messages to slots in a round, and finally, to provide admission control. In other words, when a node requests more bandwidth, to decide whether this is possible without violating any other guaranteed service. Again, I'm concentrating only on one aspect, namely, to determine when the next round starts. There are two major constraints to consider, namely real-time and energy. Here we see a small illustration of the main challenges. Suppose there are 3 plus 4 plus 5 packet streams, and we would like to transmit them in the rounds. For example, we have 5 packet streams with a period 15 and a relative deadline of 12. The vertical dotted lines are separating rounds. The first approach is to use a greedy strategy. Therefore, whenever there are packets to transmit, they are transmitted. The consequence is that we have many rounds, some of them relatively empty. Here you can see that the first 3 packets go to the first round. The next 5 packets go into the second round, and the next 4 go to the third round. Each round comes with a high energy overhead. This means minimizing the number of rounds is a major design criterion in terms of energy. And here you see the idea of lazy scheduling. We try to delay rounds as much as possible without violating real-time constraints. This way we can collect packets as much as possible and minimize the number of rounds. You see, for example, that now the first round that is delayed until the last moment, serving the 3 packets from the first set of streams. The packets from the second set of streams is divided into 2 rounds, where the second one just meets the deadlines of the second set of streams, and so forth and so forth. The idea how this works technically is shown here. Suppose that we are at time point 7 and we draw the future communication demands. What we want to know now is the starting time of the next round. To this end, we look at the times when future demands need to be satisfied. The first one is at time 13, next one at time 14, and so forth. But of course, what we also need to take into account is the transmission speed, and this we see in the next slide. As mentioned, this transmission speed is now considered in this figure, where the slope of the triangles reflects the available bandwidth. As a result, we see that the next round should happen at time 11. Is this all trivial? Not really, as we need to have algorithms that determine all of this in a resource-constrained environment and in real time. So we need to have fixed time bounds for all of these operations I just described in the last slides. This is not so easy to do and requires some novel combinations of data structures and algorithms. Finally, one needs some more or less classical real-time approaches to prove optimality of the scheduling method. Now let us ask the question whether this approach also works in practice. Here you see an experiment with actual hardware, in particular 30 low-power nodes that are connected with the mentioned protocols based on synchronous transmissions and the mentioned real-time scheduling approach. You see the bootstrapping where nodes learn about each other and synchronize. Then, based on a first set of communication requirements, you see a stable operation with 50 time slots per round. Then, there is a new stream request from a node, and you see that the protocol autonomously adapts. The same happens at phase 4, and finally in phase 5 you see a change of a deadline for one of these streams. On the bottom you see the execution time of the scheduling on the host node. Also the execution time is upper bounded formally due to algorithm and runtime analysis. But is this a competitive approach? Fortunately, there are international competitions going on, for example at the EWSN conference that is happening yearly. The setup of this competition can be seen here. Nodes try to communicate, the arrangement and connectivity structure is not known beforehand, and there are some ugly jammers around that try to non-deterministically jam specific links in various frequency bands. The details of this jamming and the structure are of course not known to the participants. In the recent years, the winners all used the presented principles of synchronous transmissions. Here's one specific result when we participated ourselves in the competition. It is remarkable that the protocol wins in all usually conflicting metrics, namely reliability in terms of the number of received packets, energy consumption, and the latency. That means how long the packets need to pass the multi-hop network. Now let us come to the next part, which is actually a bit shorter. It concerns the underlying hardware design. All what I've presented so far can be implemented with commercial components. Of course, this is not trivial due to the requirements in terms of timeliness, real time, and energy consumption. And as a consequence of this, I will now say a few words about one specific hardware platform we have been designing with predictability in mind. I already mentioned that partitioning is a major principle towards predictability. The nodes in cyber-physical systems very often have to sense, to process the data, and finally to transmit and receive wireless information. In order to avoid interference in terms of timing, memory, and power, we designed a platform where two or more components can operate jointly. The major principles have been: if you can avoid interference, avoid it. If you can't, bound it. In this case, the bounding is done by careful hardware and microarchitecture analysis, software analysis, and modeling everything using timed automata. Here you can see the models for the interface applications running, in other terms, the software. In addition, you see the various elements of the hardware architecture, including the microarchitecture of the processor and the memory. And after verifying this model and verifying time bounds using UPAL actually, then you can compare what you get with simulations. And this you can see here. As a result, you see the obtained time bounds with compared to some simulation results. This way, we can use the stateful interface bolt with many different communication processors and application processors. It's a true interface. And we can choose the hardware depending on the wireless protocol, for example, LoRa, Zigbee or Bluetooth, low energy. And we can choose the processors depending on the computation requirement. For example, if you want to do machine learning on the nodes. All of this because it's an interface with time-proven hardware and software. Hardware implementations can be very efficient. Here you see an example of a complete low-power system, including both the processors as well as the bolt interface. Everything together just consumes 10 microwatt when sleeping. Now we have been talking about the hardware and the wireless protocol. But as mentioned, we are actually interested in real-time end-to-end properties. What is finally necessary to achieve this? We need to integrate what we have seen so far: the scheduling of the wireless system, the scheduling in the individual nodes, and the hardware properties, including the interface bolt. All of this needs to be integrated, optimized, and proven to be correct. In particular, we need to schedule the communication processor, the transfer wire, the interface, as well as the task execution on the application processors. Here you see an overview of how we do that. In the center, you see wireless primitives based on everything is based on, namely the synchronous transmission and the principle of glossing. All computations and communications are scheduled using a time-triggered wireless protocol. It takes into account and considers all relevant resources in the system. To illustrate this very simply, you see on the left-hand side a very simple sketch of the schedule. Sensing is done, then we may need to transfer data via the wireless connections. Then you may do a computation. Its results are again communicated wirelessly, and then we need to execute an actuation task. The communication, as you see on the right-hand side, is done in rounds. The actual protocol is quite complex, as it allows for quasi-static schedules and multiple operation modes. The implementation is split into an offline part, where the combination of all modes is proven to be timely correct, and at runtime, the scheduling corresponds to the current mode, and it's just selected according to the predefined schedule that has been determined offline. This runtime versus compile time partitioning allows for resource efficient implementation and at the same time allows for proving time bounds. I also would like to note that the optimization itself is done using standard approaches with mixed integer linear programming in order to find an optimal schedule that satisfies all real-time constraint, but at the same time also is energy optimal. As a result, the adaptivity requirement we had at the beginning of the presentations can be met. The system is in this sense very agile, can wake up quickly, and can change gears also very quickly. As a very simple example, let me show an experimental setup where the described system has been used to control a set of inverted pendulums. Related to this, there have been also some work on the control side, and in particularly showing that the overall system has a guaranteed stability while using our low power multi-hop network and the low power processing nodes. Here you see the testbed that contains 20 nodes, everyone equipped with the bold interface, wireless connection, and an application processor. The communication is done using the synchronous transmission principle I just explained. We see actually two inverted pendulums here at positions A and B on the left-hand side. They are physically built and controlled. More inverted pendulums are actually available in the network, but only simulated in order to test, in order to determine the limits. One of the nodes is the controller, actually it's node number 18. And in other words, this one executes the overall control algorithm that is used to control and also synchronize the inverted pendulums. In the next video, you will see how one can walk around with this node number 18 without influencing the stability of the control. This would be completely impossible with all traditional systems, as during mobility, the network structure constantly changes, and therefore also the routing path, with the consequences we have seen before. Now you can see the video, but note that the speed of the video in the middle is increased by a factor of 3, so that the movement of the pendulum looks like that it's much more volatile, but this is actually not the case. It's just because the speed of the video is increased. Of course, one could now say that all of this quest for real-time behavior and reliable operation is not relevant in practice, and it's only a problem brought up by scientists. Why? Because we don't have anything else to do. Therefore, let me share a few of our own experiences in terms of real applications and deployments. As mentioned already, we are installing also sensor networks in the Swiss Alps. They are used to understand better the influence of global warming to permafrost in the mountains. And they are used to assist public authorities in early warning. Here you see some of our field sites on Jungfraujoch and the Matterhorn. All of these are, of course, very well-known, famous touristic places in Switzerland. We have, as mentioned, various modalities on these sensor nodes, including acoustic events from the mountains. We use cameras, we use high-precision GPS, and we are using crack meters. The information is then transmitted through a low-power wireless network to a base station that is also in the mountains. This information collected there is then transmitted to a huge database here in Zurich. You see here that the cyber-physical system not only consists of individual sensing nodes and communication, but also involves lots of data processing and transfer. All of this needs to be highly reliable, as scientists are relying on these data for their research, as well as public authorities for early warning. In the meantime, we collected a huge amount of data. The system is in operation since more than 10 years. I hope that you know who this is. Actually, I didn't know before I looked at it and looked for him, and it's actually Murphy. And he is known for his famous law. Based on the experience I just described, I can just subscribe to this law, as you can see in the next slide. In the history of our endeavors in various projects, including sensing in the extreme, air pollution monitoring and surveillance, we have seen many failures. This includes time synchronization, packet loss, communication disconnects, not enough energy through harvesting, sensor faults, computing faults, whatever you can think of. In our recent work, we have seen that there are more threats on the horizon actually, and they could potentially lead to non-reliable and non-trustworthy behavior. Let me just give one example among a larger set of things we have been working on recently. This example is decision making on the edge. That means decision making in the sensor nodes themselves. As I've already mentioned, we are also dealing with sensing in the acoustic domain. Whenever there is a rock fall, you can of course detect acoustic signals from the rocks. But even before a rock fall happens, you can hear cracks. And to make things more interesting, you can detect these acoustic signals that come from the inside of the rocks by several sensors simultaneously. This is called co-detection. By this, you can decide on the importance of the events, the magnitude, but you could even detect the location of these events through triangulation. The overall principle follows what we have seen before. Now, seismic sensors, wireless transmission, and data management and processing. Here you see, just as an illustration, the typical signals as they are captured by seismometers or accelerometers. These signals are captured by the nodes and pre-processed on them. Afterwards, this information is sent to the host for further decision making. But unfortunately, things are not that simple. Mountains are not the only ones who make noise up there. We have to deal with mountaineers, helicopters, wind and hail. If you would send all of this information to the host, then the nodes would quickly run out of energy. Therefore, it is inevitable to do a local decision. Was this event relevant or not? Did it come from the mountains themselves or from weather conditions or mountaineers? But this also means that the nodes need to make decisions. Remember my first slide, where we have seen that cyber-physical systems not only send, communicate and influence, but also they do data analysis and take decisions. Now, part of these decisions need to be made on the node itself. And here we use machine learning to classify acoustic signals. That means we decide locally whether the event belongs to mountaineers, helicopters, wind and hail, or whether they are relevant acoustic events from geophysical processes. And the decision is as final, because if the node decides it's an irrelevant event, it will not be communicated and processed further. But we all have learned enough about machine learning in order to understand that it is hard to provide guarantees on the correctness of classification and decisions. In my group, we are currently working a lot on the efficient implementation of machine learning algorithms on resource-restricted devices, and in particular on the learning aspect. So not only doing classification, but also adapting what they learned. With this, I would like to finish my presentation, but of course not without thanking all the people who worked with me in the last years. I also need to mention that part of this research is quite expensive, so I'm very thankful to many of our sponsors. And as you can also see, we had intense collaborations with the Federal Office for the Environment, with geophysics, with geography, and with research institutions concentrating on natural resources and pollutants. Well, this final video may be shown during your questions, or you may just enjoy our installations in the mountains. The video was actually done by the Swiss National TV for some feature they showed. And now I would like to thank again for the opportunity to give this presentation. And of course, I thank you all for your attention.